a team of researchers affiliated with UNIST, that is Ulsan National Institute of Science and Technology, has come up with a novel electrode that could greatly improve the stability of perovskite solar cells, PSCs, the most promising candidate for the next generation solar cells due to their low cost and high power conversion efficiency. This is because inserting a protection layer between the metal-based electrode and the perovskite film can prevent metal-induced degradation, and that graphene as such a layer can effectively suppress the diffusion of metals and halide ions. In their breakthrough work, the research team developed a flexible metal grid-based hybrid electrode platform by using a copper grid-embedded polyimide CEP film with a graphene sheet as the protection layer named GCEP, which exhibited high electrical conductivity, excellent chemical stability, and mechanical durability. Through this, they demonstrated the critical role of graphene as a protection layer to prevent metal-induced degradation and halide diffusion between the electrode and perovskite layer. Metal oxide based electrodes, ITOs, have been used as conventional transparent conducting electrodes, but their inflexibility causes them to be easily broken or fractured, hence making them unsuitable to wearable device applications. In particular, the major obstacle to the metal-based transparent conductive electrodes TCE application in perovskite solar cells is the degradation induced by the interdiffusion of metals and halide ions between the metal electrode and the perovskite layer. The researchers solved the problem by inserting a graphene sheet as the protection layer at the metal electrode perovskite layer interface. Graphene has high electrical conductivity, which allows electrons to move easily through it. However, the excellent impermeability of graphene prevents the permeation of even the smallest molecule. Graphene can be an effective diffusion barrier if combined with metallic nanostructures having the characteristics like outstanding impermeability to metal and halide ion diffusion at the metal electrode perovskite layer interface, enhanced charge collection across the wide spacings of the metal nanostructures, minimal loss of optical transmittance as a protection layer due to its high optical transparency, and improvement of the mechanical durability of the hybrid electrode. The researchers used this transparent and flexible hybrid electrode to fabricate flexible metal TCE based PSCs, attaining good chemical and mechanical stability. This device achieved a high PCE 64.4%, comparable to that of its ITO based rigid counterpart 17.5%. They also verified the role of the graphene layer in ensuring the chemical stability of the solar cells by preventing metal and halide ion interdiffusion. In addition, the GCEP electrode improved the PSC photostability by blocking the ultraviolet UV and near UV light. It also maintained over 97.5% of the initial efficiency even after 1000 hours. In addition, after 5000 bending tests, it showed excellent mechanical durability, such as maintaining 94% of the initial efficiency, and thus it was applicable to next generation wearable devices.